Okay, as those are going around, let's go over the quiz answers here to make sure that if you didn't learn them right, if you didn't get them right, you can learn from the quiz. So number one, static friction applies A/N blank force is compared to kinetic friction. So which feels good there? Higher? It's a higher or equal. Since that was your question, I'm glad you answered correctly. That was your question, right? I think it was. Number two, every object continues in a state of rest or uniform motion in a straight line unless acted on by a what? Not a normal force. A normal force is a force that comes out of a surface to keep you from going through the surface. And a normal force could be the thing that keeps you, or that changes your motion. For instance, if I'm falling down and suddenly I hit the ground, that normal force is going to make me change my motion. But it's not the only thing. We need the one that's going to be. So what else would we have here? A non-zero net force. That's correct. It's the net force that's important. If you have just one force, right now there's a normal force acted on me, but I'm staying in constant motion despite the normal force because my net force is zero. Third one, you're driving down the road and see a yellow light ahead. You slam on the brakes. You're obviously not related to my wife, and get launched forward toward the window. What keeps you from going through the window?
I don't want to say okay. So
Hosanna's feeling good.
What is the speed of the car? Because I think I misunderstood the question. I was thinking that the car comes to a sudden stop.
Well, yeah, that is what's going on. The car comes to a sudden stop. Why don't you keep going? Let's back up a step. What would make you keep going? Inertia. So inertia is not the thing that keeps you from hitting the window. That's the thing that would make you go through the window.
So that's gravity.
Gravity is acting downward. It's none of the above.
That's just true.
But gravity, if you didn't slow down fast enough, then gravity would keep you where you were.
Well, gravity is pushing you down.
Right.
So it's not going to affect your horizontal motion. It's only because its direction is down, it's only going to affect motion in that direction.
I'm offended. Can we not have questions like that ever again? The none of the above ones. I feel like that's just rude.
I'm sorry that you feel it's rude.
I'm never going to get one of those right.
It's a very standard answer, and it's not there just to be, okay, there's an extra spot. It's supposed to be one of the possible options. So what would it be that keeps you from going through the wind or hitting the window?
Your seatbelt.
Probably your seatbelt. Could be friction. You could brace your arms. You could have an airbag. There's a lot of things that could have been what caused you to slow down. So that's why I put none of the above, because there were too many options. The one that was turned in had the seatbelt, which would have been a potential correct answer, but it wouldn't be necessarily the only. So I just replaced it with none of the above. Which is an example of kinetic friction? It's not all, because kinetic.
It's the non-movement one, so none.
No, kinetic means the moving one.
Because
So the hockey puck is the one that's sliding.
So they all slide. They were all sliding. Table sliding.
No, because it says pushing a stationary chair. So the chair isn't moving, so it's going to have static friction. Likewise, pulling a still table. The table isn't moving, so it's going to be static friction.
So we get a drop.
Absolutely. Okay. Any other questions about the quiz?
Are all quizzes going to be like 4 questions?
Yes. Yeah. They'll all be four multiple choice questions that are written by the students.
We fail our own question on the quiz. Does that impact like the question?
No.
Grade?
No. Okay. Other things now. Go here. The little forms I had you fill out here. You have options. These are the blank ones, so I can take those. First of all, this is for returning papers other than exams. I'll never return the exams in boxes. So if you are going to give me permission to return your papers other than exams in the boxes right out here, yours will be in the top row. And I think it just has 1, 2, 3, 4, 5, 6, 7, 8, 9. So 101 would be in box 1, 102 would be in box 2, and so on. If you're going to give me permission to put them in there, then you need to check the box that says authorization granted, and then fill out this information at the bottom. Make sure you remember the number at the bottom, because you should put that on your assignments to make it easy for us to put them back in the box. If you do not wish to have your papers returned out there in a somewhat public place, right? Some nosy person could go and look in the boxes. Then check the box that says authorization not granted, in which case I will set yours aside and then just give them to you in class. So you've got the options there. And just give them to me at the end of class when you have them done. Yes?
Not about the boxes, but do you post the PowerPoints on the
Yes. And that was my next thing, Moodle. So here is the Moodle page for the class. And just for, your perusal, if you forget your syllabus or what the schedule is, you have those at the top. The lecture attendance is where you can check your attendance grade. You can also go over here, and yours will have different things and tell you, this is what your attendance grade is. I'm not going to click it because I don't want you to see other people's, even though I'm pretty sure everyone's been here every class period. Then you have some useful sites. Lecture resources. If you want to go and re-listen to the lecture from Friday, you click on this top link that says current lectures on YouTube, and it'll take you to the playlist from YouTube, and then you can choose which lecture you want to listen to. If you want to listen to lectures from the last couple years, you can click on the one for 2018 lectures, the one for 2017 lectures. Then we have part 1. That's the first part of the class. Here's the lecture material. So here's my notes for the first 3 lectures. If you wanted to see my notes for those lectures, whoops. I actually didn't mean to go to them, but you can view them there. We have the homework assignments. So here's homework assignment 1. By the way, down here, quizzes. These here are the potential test questions. They're scheduled. You don't put anything in there. It's just listed there. The quizzes are not specifically scheduled, but when they're done, then we'll put grades there. So those are not as useful as they could be. The laboratory, so if you wanted to see your report from the first lab, which hopefully you do so you can see, what did I miss? You would click there, and it'll have your uploaded graded thing so you can read it. Down here is the equations that are going to be available to you for the first exam and where the first exam will be. So let's look at this first homework assignment just real quickly before we start physics. I've spent a lot of time already. So here's the first assignment. Now remember, you can turn in on paper by 5 p.m. on Wednesday. Just slide it under my door if I'm not in there, but I'm probably going to be in there until 5. And if you choose to turn it in on Moodle, which is what I hope you will do, scan it as a PDF file, and then you upload it. So you click here to upload as well as here to get the questions. And then down at the bottom, you will have an option for submitting. I don't because I'm the teacher here. So note the banner there in red. Important, unless otherwise noted, for credit, you must always give an explanation for how you got your answer. If a calculation is involved, you must show your calculation. Just having the answer won't earn you credit, right? Because a lot of times, it's asking the question, what's the net force? You put 5 newtons and go on. How do I know that you didn't just ask somebody, hey, what's the answer? And they said 5 newtons. Or you looked in the back of the book and it said 5 newtons, right? I need to see evidence that you thought it through and did the work. Yeah.
Wait, did you say the answers are in the back of the book?
For some of them, they are, yeah.
For some of them.
I don't remember if it's evens or odds or what. But yeah, there's answers for some of them in the back of the book. So, and, you know, I mean, other people could, you know, there's always Chegg out there. A lot of people will cheat. They'll go to Chegg. Don't do that, okay? Cheating is not a good thing. Do the answer yourself. If you have questions, ask somebody to explain it. There's always me. I'm happy to explain things. And remember, my office hours are in your syllabus and they're on my door. Anytime you see me, I would be happy to help a student. So just looking at these, notice the first question. What name is given to the property by which objects resist changes in motion? This one does not need an explanation, just a single word. So that one there, you can just put the correct word and you're done, because it has a specific statement. You don't need an explanation. The next one, a 1 kilogram object weighs nearly 10 newtons on Earth. Would it weigh more or less on the moon? You can't just put the same more or less. You have to give it a reason why it's the same, or why it's more, or why it's less. Is that clear to everyone? Okay. I don't want confusion. I don't want people to say, I didn't understand. I thought that I could just say blank. Okay, so here's all the questions. And so there's 12 questions. Obviously, you can copy those, paste them as you like for whatever format you want. Did you have a question, Bryson?
Yeah, on number 9.
Yeah.
How are we supposed to explain which net force was greater? Because it's just, I mean, net force is just like when you have the strongest amount of newtons. So like on A, for instance, you would have 5 newtons pointed to my left.
Okay, so on A, you would say 10 newtons left plus 5 newtons right equals 5 newtons left. And for B, 7 newtons left plus 3 newtons right is 4 newtons left.
Oh, so we would just
For C, 12 newtons left, 4 newtons right is 8 newtons left.
So we would just write
This
out
one
like
here,
the
3 newtons left,
equation.
you'll see 8 newtons right is 0. And then put them in order.
And you would consider that an explanation?
Yes. Yeah. Yeah, if you show that you know how you got the net force for each one. But if you just put them in order, right? I mean, I can look at this and say, well, the correct answer from greatest to least is CABD. So if you just put CABD, well, that's not going to cut it. It's nice when they're simple like that. They won't always be. All right. Going on to the actual lecture material. The pen was working correctly before class started, just, for the record. Still is. Good times. Okay, a question you've already seen. Just reviewing this question to make sure that we remember things from one week to the next. When Nellie pushes a crate across the factory floor at constant speed, the force of friction between the crate and the floor is which one? It's equal and opposite, yes. Just like we had on the quiz today, the net force has to be 0 for it to be constant motion. So equal and opposite to her push. And that was Newton's first law, said that you have to have the net force is 0. I didn't mean to leave these 2 slides in. I'm not sure what happened. I thought this was, I wonder if I have, no, it started the right place. I just made a mistake. I could have sworn I deleted all of these. This is what was supposed to have been the second slide. If you swing a stone overhead in a horizontal circle, and of course I won't do it with a stone, I'll do it with a stopper. So I swing it around like this. That's what it means. And the spring breaks. What direction is the stone, or in this case, the stopper, going to go?
Out.
Okay, Hosanna says out. Can you be more specific on what out means?
Towards one of our faces.
Towards one of your faces. I will try not to make that happen. Yes, Grace.
Would it be like a curved path? Because of the fact that it's going a curve
Okay.
right now.
We have suggestion of a curved path into the face and out.
I see a straight line. I was straight line. I see a straight line.
Okay, we have 2 people that counted with a straight line. What do you say, Lindsay?
Spiral.
A spiral path. Okay, it is up there. Okay, Okay, so we have some variations here. So let's first, we're scientists, right? Yes, for this class's purposes. So what we do in science is we experiment. We don't say, oh, it's going to do this, the end. We say what we think it will do, and then we test it. So I'm going to start just by seeing what it does with observation, so we can do that. So I'm going to let go, to the best of my ability, when the, what direction should I, you guys tell me. Where should I have this when I let go? Okay, so everyone disagrees. Okay,
The direction with no people.
That way, because there's no people or computers.
I'm gonna try to stop it when it's pointing directly away from you guys. Okay, guys, I'm gonna let go when I say stop it. So I'm not perfect. It may not be right at the right time. Whoops! My finger caught it when I was just trying to gauge my positioning with my hand. Nice job, huh? We'll do it again. Stupid finger. We blame the finger, not the person. Okay, so it was in that position. I let go, and it went straight. He was right. It did not curve at all. And I know it's too fast to actually see if it curved or went straight, especially from the angles we're looking. But now let's talk about it in theory. So it was going around in a circle. And right when it was here, I let go. What direction was the motion at the moment I let go? If it's going around a circle like this, what direction was it going right here? That way. So it was going this way. I put a V with an arrow over it. That means I'm showing the speed with the direction, otherwise known as the velocity. So the arrow means it has direction with it. So it was going that direction. Once I let go, in the vertical direction we had gravity, right? So gravity is going to make it go down. But in the horizontal direction, once I let go, there were no forces. There was nothing pulling or pushing on it. And so according to Newton's first law, what happens if there's nothing pushing or pulling on an object? Keeps going in a straight line. And so according to Newton's first law, it should have just kept going in that direction, falling because of gravity, but going that direction horizontally. Not curving because it would have required a force to make it curve. Now, remember, somebody said curve, and I said it didn't curve. If we're talking about the vertical direction, yes, it curved downward. So we have to be clear. We'll learn soon enough that we can take perpendicular directions and treat them separately. So I've been doing this since before you guys were born. In my mind, it's just so clear. Yeah, I could just ignore the vertical part, and then I forget, well, no, you're thinking about the whole 9 yards, not just the horizontal part that my brain is doing. So in the horizontal direction, it's going to be a straight line path going the direction that it was traveling at the time I released it. So if I wanted to, let's say, hit Jessica, because she was the one who specifically said that it was going to hit one of us in the face, which of course I'm not going to do this. If I wanted to hit Jessica, when should I release it?
A 90-degree angle from her.
Okay, 90-degree angle from her. So since you're this direction, I need it to be that direction. If I let go when it's in that direction, its velocity would be like this and go over to hit you. Crazy. It's fun. When I was a kid, you guys know that I lived in Liberia until the age of 5, right? I grew up in Africa. And one of the things we had as play toys was slingshots. Let me tell you, people who know how to use slingshot can be really amazing with them. They would set up like a tin can, different points in their rice fields. And to keep the birds away, the lady would take her slingshot and get a rock, much like David, go and hit a tin can with the rock. The tin can makes a noise and the birds fly away. That way they could keep birds away from the whole field without having to go all over the place. pretty ingenious. And so that was one of my toys as a child, was the old slingshot, which, yeah, we loved. Which is probably why They Might Be Giants has a song about everybody wants a rock to wrap a string around. You guys don't know that, right? No. Because They Might Be Giants were popular about the same time you were born. I meant to take this one out too. Something didn't go right with my editing. As God is my witness, I took them out. But I probably saved it before I took them out or something. I don't know. If you're in an airplane, we've probably all flown in an airplane. If you're in an airplane, you could take, let's do something a little more reasonable than flipping a coin. They give you peanuts often. You can take those peanuts, toss them up there, and catch them in your mouth, right? I mean, if you could do that staying at home, you can do it in the airplane. But the airplane is moving really fast. How is it that it works that you can do that when you're in the airplane when it's moving really fast? The peanut has inertia. The peanut's moving the same speed you are. It's going to keep at that speed unless something acts on it. You tossed it up. You made an upward force, and it went up. Once it left your hand was no longer applying a force to it. It continued upward because of the inertia it had from you tossing it. But gravity was acting against it, so it comes back down. And so as long as you're not hitting turbulence, everything's going to be the same if you're traveling in the airplane than if you were just sitting in your kitchen. I wish this was working.
Well, what if you let the peanut fall long enough? Like, you couldn't do this in an airplane because the cabin's only so big, but eventually it would come to a stop, right?
Okay. Absent air resistance, first of all. Right? We're going to pretend there's no air resistance.
Yeah.
If you were tossing the peanut up and it comes down and you miss it, it just keeps going down, it would just stay right with you as you travel horizontally the whole way until we have to start worrying about the curvature of the Earth.
Yeah.
We have this thing called the Coriolis effect. Coriolis effect is the reason that weather systems always rotate the same direction in the northern hemisphere and the opposite direction in the southern hemisphere. And that's because the Earth is rotating, and if you're farther away from the center of rotation, you'd have to go the same speed or a faster speed to stay over the same place. And so there's that effect. Is that what you were talking about? Yeah. So, for a class like this, we generally are going to ignore that because you have to have a pretty significant distance to move to see the difference. So this question here, I left this one in, and I'm thinking he might have put this in because of flat earthers. You guys have probably seen on Facebook a lot of people talking about the Earth being flat. And one of the arguments that is used by flat earthers is that if the Earth is a ball, they think it's pejorative to call it a ball. I don't know why it's pejorative, but they do. And that ball is spinning, then the surface of the ball that we're standing on is going really fast. Do we feel like we're moving really fast? No. And they suppose that we should feel an incredible breeze because we're moving so fast. And the bird, if the bird hops out of the tree, it should go flying to the side, is again another thing that they propose. Why can the bird just drop down from the tree and hit that worm instead of going flying off? Go ahead, Grace.
There's two things. Like, the bird is like moving like at the same rate as the worm, so it's not like it's going to be coming at a different time, because it's like while the Earth is moving the worm, the Earth is also moving the bird.
Right.
And then also like the Earth is accelerating like it's like a constant rate. So like we can't feel it because it's like constant speed. So it's just like being in an airplane and you're like going really fast.
Okay. Let's keep away from the acceleration just a little bit. There was a little mistake there, and it confuses the issue here. But the first part was dead on. The worm is moving, the bird is moving, the air is moving. The air is moving with the surface of the Earth, which seems pretty obvious, right? The water is too. We don't have oceans flying all over the place. They stay what appears to be fixed with the Earth because they're rotating with the Earth. Because there's friction. We talked about, you have your hand out the window and you feel the air resistance. Well, with the Earth spinning, there's friction with the air, and it pulls the air so that the air reaches equilibrium, rotating with the Earth. At the surface, you go up higher, and you have some variations. So you have things that we call the jet streams that are not going the same speed as the surface is when you go up higher. So the air is just moving with the Earth. That's why you don't feel this incredible breeze, because we're moving so quickly. So I like this one because it helps us to understand a point that, the flat earthers are, by and large, very, very non-knowledgeable about science. And so help us to understand this better. And so there it actually shows if the Earth moves at 30 kilometers per second, 30 kilometers per second is cooking, right? Yes, flat earthers also think that I should be able to jump up and, travel from here to California. And just, if the Earth is rotating, it shouldn't be a problem. Okay, here to California? Yeah, that's right. Because, I would only travel 30 kilometers in a second, and I'm probably not going to get much more in a second. But still, 30 kilometers, that's a nice hop. Yeah, I'd be at least past Crete. Anyway, moving on. Newton's second law. So far, we've talked about the first law, the so-called law of inertia, that says an object will stay in constant motion. That means, as Grace said in her quiz question, constant speed with a constant direction or something to that effect, unless there is a non-zero net force acting on it. Newton's second law gives us an equation for what happens if the net force is not zero. So Newton's second law says that if the net force is not zero, it's going to accelerate, and the acceleration relates to the net force and the mass. So in the same direction as the net force, proportional to the net force, and inversely proportional to the mass. Now, of course, I said it gives us an equation. Those are words, and they're words that we should understand. Proportional means that if you double the force, you're going to double the acceleration. That's what proportional means. You triple the force, you're going to triple the acceleration. It's a linear relationship, as we say mathematically. So from the first statement here, we can say that the acceleration is equal to some constant times, and I'm going to put F with the subscript of net. F with the subscript of net, that means net force, and it means exactly the same as a sigma, which stands for summation, somebody asked this last class period, times force. So we have from our first statement, so I'll underline what I've just done. We have the acceleration proportional to the net force. That's what I've done so far. I'm not done yet. Then we have in the same direction. How do we indicate direction with our symbols? Yes. So in the same direction, so I'm putting the arrows over there. The acceleration direction is going to be the same as the net force direction. I can now add in, so that's what the purple arrows are telling me. And then finally, I actually don't want to use that color. Too late now. Finally, I have inversely proportional to the mass. Inversely proportional means it's related to 1 over the value. So I need to take this and divide by the mass. And that's Newton's second law. So you can see the words play out into an equation. So what do we do with Newton's second law? We say net force is mass times acceleration. Or we write an equation like this. We never read out all of those words because it can be said very succinctly as a mathematical equation. So for Newton's second law, it is really important that you have net force. You so often, and I think even our textbook, you often see F equals ma. Well, F equals ma is just wrong. You can't defend it. Because, I have a force normal acting on me. The force normal is upward. I don't have an upward acceleration because it's the net force that's going to make the acceleration, not one of the forces. So you do need to have net force. So this is our Newton's second law equation. So here it's written out in nice big bold letters, and you can see I wrote the net force two different ways for you, just to help you develop comfort with both of them. That Greek sigma, the thing that looks like a funny E, means adding them all up. So on the right side we have sigma F, adding up all the forces or sum of the forces. The middle we have force net, which means if you added up all the forces. The arrow on top means they're vectors. It means the directions are taken into account. You're not just adding the sizes of the forces. You're not saying, oh, there's an upward force of 10 newtons and a downward force of 10 newtons. You don't say the total force is 20 newtons. It's going to be 10 up plus 10 down, which would be 0. And then we have different size fonts to indicate a big force is going to cause a big acceleration. A big mass will lower the acceleration. So I think I mentioned in class the other day about baseballs, throwing this versus throwing this. If I put the same force on these two objects, which is going to respond with a bigger acceleration? The tennis ball. Why?
Because it has less mass. So.
Less mass. Less mass, there's less material here. This one here is much more material. So for the same force, this one's going to respond much more, accelerate much more than this one will.
Would it be correct to say it has less inertia?
Yes, because mass is proportional, or mass is a measurement of inertia. So less mass and less inertia mean identically the same thing. All right, now we're going to talk about free fall. I think one of our homework questions, it was one of the questions the student asked was about the definition of free fall. Free fall being when there is nothing but the force of gravity acting on an object. So let's look at, here's an object, and if it's in free fall, that means the only force acting on it is in the force of gravity. So I'm going to draw.
Force of air resistance isn't.
Right, we're ignoring the air resistance unless we're told to include it, which will be extremely rare for this class. And we know it exists. And so in real life, we have to take it into account. But in our learning stages, we're trying to simplify. And even in general physics, we generally try to simplify it.
So, I'm sorry, this is still kind of off the topic, but if it was going up, like say someone threw it up, and then it fell, like right when it immediately started falling, should we assume it's falling at 10 meters a second?
Let me answer this question after I'm done with this, because it's a really important concept. It's not off topic at all. So let me finish this and then I'll answer that, because it's super important and it relates to this. So if that's the only force, then I can determine the acceleration by applying Newton's second law. Now notice that force is downward. If I put vectors on here, the force vector is m times the g vector. The g vector, our textbook uses 10 meters per second squared. I always say 9.80 meters per second squared because, well, it's correct. But the g vector is pointing down. So it has a magnitude, how big the number is, 9.8 meters per second squared. It has a direction down. Now, if I take Newton's second law told us that the acceleration vector is equal to the net force vector divided by the mass. So I look at my picture and I say, what are all the forces? Because I want to add them all up. Well, there's only one, so it's kind of easy to add them all up. So I'm going to replace the net force with its actual value. And then divide by the mass of the object. And lo and behold, what is the acceleration going to be? Okay, I'm just going to put g, but you're absolutely right. It's going to be 9.8 meters per second squared. In what direction? Down. So if I have an object in free fall, combining the ideas of the force of gravity is mass times acceleration of gravity, and Newton's second law, we can say that anytime it's in free fall, it's going to have an acceleration of 9.8 meters per second squared down. Now this is where I'm going to deal with Bryson's question. So first of all, if I throw the ball up, when does free fall begin? After it leaves your hand. Once it leaves my hand is no longer pushing or pulling on it, so it's free then. So the free fall begins after it leaves my hand. So the moment after it leaves my hand, it's a free fall, what direction is its motion? After it leaves my hand, it's up. The instant after it leaves my hand. What direction is its acceleration? Not up. During free fall, the acceleration is going to be g vector, which is always pointing down. So as soon as it leaves my hand, its velocity is up, its motion is up, but its acceleration is down. What happens if the velocity and acceleration are opposite directions? Now, before you answer, I know some people know the answer. What does acceleration mean? It's the rate in which the speed is changing. So if the speed is, well, the velocity, I have to use the right term occasionally. If the velocity is upward and the change in the velocity is downward, then what's going to happen to the velocity? It's going to decrease because it's changing downward, opposite direction. So as it goes up, because it has a downward acceleration, it's going to slow down. Now when it's coming down, what direction is its velocity when it's coming down? It's inherent to the question, but you have to ask to make sure that everyone's clear that it was in the question. What direction is the velocity when it's coming down? It's down, because when it's coming down, velocity is the motion. It's coming down, velocity's down. So it's coming down, the velocity's down. What's the acceleration when it's coming down? What direction? Down. Because throughout the entire free fall time, its acceleration is 9.8 meters per second squared down. So now its velocity is down and the acceleration is down. If the velocity and acceleration are the same direction, what's happening? It's going to speed up. When the two are in the same direction, it's going to go faster. And so as it's coming down, its downward speed is increasing. And once again, we're ignoring air, just in case that's what you're going to ask. Okay, what would you say?
Is the rate of acceleration the same whether the ball is going up or down?
If we ignore air, yes.
Okay.
Right? If you don't ignore air, the answer is obviously not. Okay, so we've established velocity up, acceleration down means it slows down. Velocity down, acceleration down means it speeds up. What about at the peak of its flight? At the peak of its flight, what is its speed going to be? 0. At the highest point, it went from going up to going down. And the place where up and down meet is not moving. So its highest point, its speed is 0. What's the acceleration at that instant? This is an often missed question. If you blurt out the wrong answer, don't feel embarrassed.
Can you repeat it?
Yes. At the very peak of its motion, its velocity is 0. Or excuse me, its velocity is 0. What is its acceleration?
Down.
Okay, Bryson says down. Does that sound right?
Wouldn't it just be nowhere?
Okay. Hosanna says, wouldn't it be nowhere? That'd be a way of saying 0.
Yeah, it's around.
How do you guys feel? Obviously, one of them's right. Well, not one of them's right, but one of them has to be wrong since they have two different answers. How do you guys feel?
More with the 0.
One with the 0? Okay. The 0 is incorrect, but I told you this is very often missed because of a very simple thing. We know acceleration has to do with speed. We have an accelerator on the car, and we start thinking of speed and acceleration as the same thing, but they're not. Acceleration is the rate at which speed is changing. So it's instantaneously a speed of 0. If the acceleration was 0, how much would the speed be changing? It wouldn't. So if the speed is 0 and the acceleration is 0, what's the speed going to be a moment later? 0. And it's just going to stay 0. So if the acceleration was 0 at the top, you get to the top and it would just hover up there. But the fact that it falls down means that the speed is going to be increasing in downward direction. What do we call the increase in speed? The acceleration. So it has to have a downward acceleration. And once again, during the entire free fall time, it had the acceleration of 9.8 meters per second squared down. So while it was going up, the acceleration was down. While it was coming down, the acceleration was down. And at the peak, the acceleration was still down. Is that making sense now? Obviously, it's not what a lot of people were thinking, but I firmly believe it's not because people actually thought the acceleration was 0, as they were confused about what acceleration is with regards to speed. You get speed and acceleration confused, I believe. Any questions on it before I move on? Do remember, I see people already have written their potential test questions. We need potential test questions for each lecture, so today is another day, another potential test question. This here is a picture to relate now exactly what Galileo's Leaning Tower of Pisa thing was all about. According to what we've learned, if I have 2 bricks versus 1 brick, the force of gravity on 2 bricks is going to be 2 massive bricks times g, so twice as big as the force of gravity on 1 brick. What's the traditional word we use for the force of gravity? We do have that, but in everyday experience, you don't say, oh, well, the force of gravity acting on me is this. What do you usually say? Okay, you probably don't talk about it very much. My weight is this. Right? Force of gravity is weight.
I avoid that conversation at all costs.
Yeah.
I had no idea what you were talking about.
So if you have 2 bricks, you have twice the weight, but using Newton's second law, if you take twice the weight divided by twice the mass, you get the same acceleration downward. So regardless of the mass of the bricks, 1 brick, 2 brick, 5 brick, they all are going to have a downward acceleration that's the same g. Assuming no air resistance. So I'm not going to go to it. I actually have it there for you to watch, a link to it. But the experiment with a feather versus a rock. Here on Earth, if I take a feather and a rock, which I can take a tissue paper and my ball, if I drop them, you can tell me beforehand, based on your previous experience, what's going to happen if I drop the 2. The ball drops much faster. Because of air resistance. So Galileo said, if there's no air resistance, they'd be the same. And here, which you can view if you go to the presentation on Moodle after I've done it, there is a video, okay, I did pull it up here, where an astronaut actually did this experiment. But I'm actually, well, it's not very long. I'll go ahead and play it.
We got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Okay, and that ends the day.